All right, let's get this show on. Hello, everyone. Hope you're well. Welcome to another installment of Math 391. I still have some people trickling in here, but let's actually jump into it. So we kind of ended off with some examples last time. So we're going to finish those guys off. We're going to talk about some new stuff and then hopefully get to some more examples. Take a sip on my coffee here. All right, so we've been talking about finding power series solutions to ODEs. And we saw that if we have something like this, we can assume a solution looks like this, and we can differentiate power series and all that good stuff. We can plug them in, and we can get a power series solution under the right conditions. So we saw some of those. I asked you guys to try some of these for next time, and we had those, and we did some examples going through that. Hopefully you remember. If you don't remember, we're going to do some more examples right now. So hopefully that will jog your memory. So we had these two to cover. So the plan for today is I'm going to cover these two examples using basically what we did before. I'm going to show you a slight variation on this technique that could make your life a little bit easier in some situations. And then I'm going to talk about a whole other way to find power series solution, assuming that our power series solutions can be described by Taylor series. Then I'm going to talk about something called Euler's equations. And class will probably end at that point. But if not, I would move on to continue to show how, using what we know about Euler equations, we can find power series solution at singular points, specifically regular singular points. So I'll remind you guys of what that is when we get there. But for now, let's actually just get through these examples. But that's so the plan for today. So started here. Okay. So this next example comes courtesy of the math department. This was actually on a department final. So this was on the fall 2011 final. This was on the fall 2011 final. So you can see a question as it was asked to students of that year. For the differential equation blah, compute the recursion formula for the coefficients of the power series solution centered at x naught equals 0. Use it to compute the first 4 non-zero terms of the solution with these initial conditions. Okay, so here they ask for a power series solution. They only want the first 4 non-zero terms. Let's actually jump into it. So the first thing is we assume y looks like a power series solution centered at x naught equals 0. So this is like a n x to the n because our x naught equals 0. Now this means we can go and we can plug it into the ODE, right? So the ODE was 3 minus x times the series of the second derivative. N minus 1, a n x to the n minus 2, plus x squared times the series of the first derivative, n a n x to the n minus 1, plus 1 plus x times the original assumed series. Okay. So that was our first step. We plugged it in, and now the goal is to actually find the ANs so that we can get the coefficients. This is going to involve us like expanding these series and all that good stuff. So let's just jump into it. So here, this would look like, well, the series from 2 to infinity of 3n n minus 1 a n x to the n minus 2 minus the series when I put in the x plus this series here. Notice that when I multiply in the x squared, it's going to bump up the power of x by 2. So this now becomes x plus n plus 1. Plus expanding that 1 times this series. Plus x times this series, which bumps up the power by 1. So we have that. Okay. Next thing we do. What is the next thing that we try to do? What is the next thing we fix? Let's see who's can tell me what's the next step. What is the next thing we look for? Fix the powers. You want to fix the powers. Get all the powers to look like n. We can do that by doing a shift. So notice that I will need to shift the first series, the second series, the third series, and the fifth one. So lots of guys. So in the first one, I would let n go to n plus 2s. So this will now start at 0. It's 3n plus 2 times n plus 1, a n plus 2 x to the n, minus this second one. I would let all the n's go to n plus 1s. So this will now start at 1 to infinity, n plus 1 times n, a n plus 1, x to the n, plus this I'll shift all the n's to n minus 1s. So this series now is going to start at 2, n minus 1, a n minus 1, x to the n, plus this series is fine. Plus this, shift all the n's to n minus 1s. So this is going to be the series starting at 1 to infinity, a n minus 1, x to the n equals 0. So that's where we are. So now all the powers look like n. Now what we have to do is make sure that they can start at the same point. Now, this one we could start at 0. Because when I plug in n equals 0, it just adds 0 to this whole thing, so that's fine. This one, notice that it's okay to start at n equals 1. Because if I plug in n equals 1, that will give me 0, but everything else will be fine. However, if I plug in n equals 0, I do get a non-zero term here that I have to worry about, but we'll talk about that actually a little bit later. You'll notice that when your n is 0, you get minus 1a to the a sub minus 1 and x to the minus 1. We'll talk about that observation a little bit later. What happens to the coefficients when the subscript goes negative? This guy's fine, he's already starting at 0. This guy is starting at 1. And starting at 0, again, I run into this issue with the subscript. I would get a n minus 1, a sub minus 1, which is, it's kind of weird for what we're doing. And technically that term doesn't exist in our conceptualization of things. So what happens is, I have a bunch of series that can start at 1, and then I have a bunch of series that I start at 0. So the next thing is to get all these series to start off at the same point, because again, remember, I want to actually combine these series. What I can do to combine the series is evaluate terms. So this goes to a step that we previously have never used before. Evaluate terms. Evaluate a term in the series that start at n equals 0 so that we can start all series at n equals 1. So that's what we're going to do. So going to the first series, if I plug in n equals 0, so if I plug in n equals 0, for the first series, I would get 3 times 2 times 1, a2, x to the 0, plus for this series, so I'm doing for this series over here. That's this term here. This guy here at 0, he would just give me 0, so I can even ignore that. This guy here, he already starts at 1, so I won't care. This guy here starts at 0, so this is a series. I'm going to evaluate some terms. The first term here is going to be a0 x to the 0. So that's me evaluating the first term from that series. And so I have those two guys here. Now plus, now I can start all the series from 1 and combine everyone. Because they all have the power x to the n, and they all start from 1. So now I can actually start grouping all these guys. 3n plus 2, n plus 1, an plus 2, minus n plus 1, an plus 1, plus n minus 1, an minus 1, plus an plus an minus 1. Now, again, we have to set the coefficients equal. To match the right side. Which means we have something immediate. You see from the first part, when I evaluated n equals 0, I get 6a2 plus a0. That must be 0 to get, because there are 0 constants on the right side, there must be 0 constants on the left side. Right? And this is, it's a little small. Let me write that a little bigger. So there's a 0 on this side over here. Okay. So that must be 0, which means right away, you know that your a2 is going to be a0 over 6. So that will come in handy later on. Then to find the recurrence relation, I'm going to set everything inside these brackets equal to 0. So I would have to obviously solve for the an plus 2. To get that, I'm going to have a bunch of terms divided by the coefficient 3 times n plus 1 times n plus 2. So what I would get, moving this guy to the right side, he would be a plus n times n plus 1, a n plus 1. Then I would have a minus n minus 1, a n minus 1, minus a n minus a n minus 1. And so I would get that by setting those guys equal to 0. So that's the recurrence relation. I mean, we can clean this up a little bit, can we? Let's actually clean up a little bit. I mean, I can combine this n minus 1 in there. Right, because this guy will actually cancel. This part would cancel with that if I multiply it out. Right, so this would look like n times n plus 1, a n plus 1, minus n a n minus 1, minus a n, all over 3 times n plus 1 times n plus 2. So that's the recurrence relation. They asked us for that. Find the recursion formula. So this is the recursion formula. Now, we want to find, what did they ask for? Compute the recursion formula and find the first four non-zero terms. So now our A0 is equal to -6. Our A1 is equal to 2. Our A2 is equal to A0 over 6, which is -1. I can get that from here. Also notice from the recursion formula, so this is from this equation here. But notice from the recursion formula, we should essentially get the same thing. Recursion formula would be n equals 0 in this formula. It's kind of weird though, but I'll just mention it again. This gives us n equals 0. This would lead us to A2. This would give us minus A0. Wait, there should be a minus A0. Because I brought that over to the other side. So this is actually a positive one. So the nice thing about that is it coincides with what I know I should have gotten, right? So this coincides. So coincides with the terms we evaluated. Now at this point, you probably don't see this, but this is going to lead to a very nice method later on. Because something like that is always going to happen. Something nice later on. So I'm going to actually redo this example. I think this exact example here, but with a little bit of a variation that takes into consideration that the terms that you would evaluate to get all your series to start at the same point, they'll actually coincide with your recurrence formula anyway. So then it makes you think, do I really have to evaluate those terms? Is it really actually important getting all the series to start from the same point? It turns out that in some sense, the answer is no. But to fit with our theory for what we know about series, we had to get all the series to start at the same point in order to combine them. But we'll actually get there. We'll actually get to something cool later where we realize that we actually don't need to worry about it. So here I need the A3 term for the non-zero, for the first four non-zero term, because here I have 1, 2, 3, 4. I need 4 terms. So here I'd plug in n equals 1. And since I keep scrolling up and down, let me just actually. Copy this. Okay, so I'm plugging in n equals 1 into that formula. So this would give me 2. This would give me 2A2 minus A0 minus A1 all over, if I plug in n equals 1, I would get 3 times 2 times 3. Okay, so that's what I would get. And now what I'm going to do is I'm going to plug these guys in. So my A2 is actually 1. So that's just 2. My A0 is minus 6. So this will become plus 6. My A1 is 2. So this is minus 2. So of course the 2's cancel. And I'm left with 6 over that. And so now you just realize that that actually simplifies to a third. So now I can write down my series solution. We only care about the first 4 non-zero terms. Our A1 was -6 from what I recall. A0 is -6, A1 is 2, A2 was 1, and A3 was a third. So this is actually our solution. First 4 non-zero terms of the solution. So, I mean, we covered this yesterday. So any questions on what happened here, or did you guys get the same thing when you tried it, or whatever? Any issues that I need to deal with at this point? Seems not. But one thing that's nice about this this example, oh, when I evaluate what? You mean this process here? Oh, well, that's because in order to combine series, the series property says all the series have to start at the same point. This first series here started at 0. This series here could start at 0, but this one starts at 1, and I couldn't bump it back to 0. This one also starts at 1, and I can't really bump it back to 0. So it turns out that these two series here, this one and this one, actually begin at 1. So in order to combine all the series, I need to get all of them to begin at 1. So how do I get the series to start at 1? Well, this goes back to something we covered last class here, right? Whenever it's convenient, I can actually just evaluate a few terms of a series so I can start it at a later point. So I can start the series at 1 by evaluating the 0th term, and I can start at 2 by evaluating the 0th and the first term, and I can start at 3 by evaluating the first 3 terms, and so on and so forth. So I can actually change where my series is starting by evaluating some terms of the series. So that's what I did down here. So to get these series here that start at 0, to get them to start at 1 so they catch up to this guy, I plugged in n equals 0, and I got this, and I get these terms that you see over here. So once I do that, I could I evaluated all the terms that have to start at 0 to get them to catch up with the guys that start at 1, and then I can combine the series. So that's what happened there. So it's when I want to combine to one big series, I need the same index, I need the same starting point. So that was, I needed all of them to start at 1, and that's why I evaluated some terms. As we saw though here, that when I evaluated the terms, it did actually coincide with the recurrence relation. So it turns out that for this kind of process, you actually don't need to evaluate the terms, but theoretically, you need to actually look at it from a different angle, because the combined series, as I'm doing, you need to evaluate the terms. And that's that one. Let's do one more example for good measure. This is an interesting example because they show up from time to time. We're going to realize that we started off trying to find a power series solution here, but we're going to realize that it's actually unnecessary. There's a nice solution to something like this. And this, by the way, has a very nice form. It's very close to something called a Chebyshev equation. Anyway, let's actually look at this one. So let's say, here's a problem. You want to find a solution, a power series solution centered at 0. How would you do it? Well, like always, so just to run this through again, assume our y looks like a series solution centered at x0. This means I can plug this into the ODE. The second derivative will be the series starting from 2 to infinity of n times n minus 1 an x to the n minus 2 minus 4x times the series starting at 1 of n x to the n minus 1 plus 6 times the series x to the n equals 0. Again, I'm going to expand this. So we have that. Now I want to see, can I start these guys all the same? Starting this one at n equals 0 is fine. Because if I plug in 0 for n, it wipes everything out, I get 0. If I plug in 1 for n, it wipes everything out at 0. So starting at 0 is equivalent to starting at 2. For the same reasons this guy, it's okay to start at 0. For the same reason this guy is okay to start at 0. Because if I plug in n equals 0, it wipes out everything. I just get 4 times 0 times blah, blah, blah. That whole thing becomes 0, so it's like I'm adding 0. So starting everyone from 0 here is fine. So I can just immediately jump to finding one big series starting at 0 of the entire shebang. So this is n minus 1 an. Oh, I actually have to shift the powers. Forgetting the strategy. The powers are bad. This is what we forget when we forget to obey the strategy. This guy is actually a problem. We need to shift that. So at this point, that's premature. Now here, if I shift all n's to n plus 2's, that's going to give me starting at 0, n plus 2, n plus 1, an plus 2, x to the n, plus, everyone else will stay the same because I don't have to. Everyone else will stay the same because I don't have to shift anything. I don't know, the time it takes me to copy everything, I don't know if I could have just rewrote everything already. So I just copied everyone back because they're all the same. So now I realized that I could start this at 0 if I wanted, because that was okay. So all my series start at 0. And then I can combine it into one big series. N plus 2, n plus 1, n plus 2, plus n times n minus 1 an minus 4n an plus 6n x to the n equals 0. Yeah, intro warned me that I was forgetting to fix the powers. That's good. One of us is paying attention. Yeah. Sometimes my ambition gets the best of me. Like I know in my head all the things I actually want to cover today, and so like my mind is like, we got to get there, and I'm just rushing. Like this is what happens to students in exams. They're just like, oh my God, time's running out, and this is how mistakes happen. However, a lot of the times, if you because you train yourself and you write things down, like sometimes I felt like I was doing something wrong, just like from muscle memory. So I wrote down the line and I realized, oh damn it, I didn't actually shift the powers. Like even I didn't even notice that Insha mentioned that while I was doing it. But it's because I've done so many of these problems. Like shifting the powers is a part of, like if I don't write down with my hand a shift of the powers, I feel weird. I feel like I've missed something. And that's kind of where you want to get with your math. I mean, it wasn't intentional, but since it happened, I can now like use this to give you a life lesson or a math lesson or something. Like how you know that you've practiced enough math is when that happens, when you physically can feel when you do something wrong. Like I didn't feel right about what I wrote down. I'm like, wait, oh yeah, I forgot to do that. Okay, so let's actually continue. Now, of course, the next step is to find the indicial equation, the recursion formula. So this is going to be n plus 2, n plus 1, an plus 2. By the way, this is all times an. So I can have n times n minus 1 minus 4n plus 6 equals 0. What does this simplify to? This here simplifies to n squared minus 5n plus 6. Does that actually factor? Right, it does factor, but still it doesn't factor into anything convenient. I mean, it's not going to allow me to like cancel anything or simplify anything. But okay, it factors. I mean, that's nice to know. So now we're always start solve for the largest index, remember? So I am going to bring this over to the other side. It's minus n minus 3, n minus 2, an. Then I divide by the n plus 1, n plus 2. This guy here is your recursion formula. So now we can find the terms. So A0 and A1 are themselves A2. These here are your y of 0 and your y prime of 0. But those were not given for this problem. So let's actually continue. Now, if I try to find A2, this just means I'm going to plug in n equals 0 into my recursion formula. This will give me minus 3 times minus 2 times A0 over 2. So that just becomes minus 3A0. Okay, my A3, here's where I would plug in n equals 1. Might carry this guy with me. Here's A3, I'm going to plug in n equals 1. And that would give me minus 2 minus 1 a1 over 2 times 3. That gives me minus a1 over 3. a4, I'm going to plug in n equals 2. Notice that the numerator has an n minus 2, which means that will give me 0. Also notice that for a5, I would get n equals 3, and that would also give me 0. Now my a6, this depends on a4. That's going to give me 0. A7 would depend on a5. That's going to give me 0, right? This gives me 0 because of a4. This gives me 0 because of a5. Because every new thing is going to give me based on something 2 steps behind. That's here. So notice that I'm going to have an equals 0 for my n greater than or equal to 4. Which means the solution is a finite series. Oh, interesting. So it turns out you don't need an infinite series to actually solve this ODE. You start out with that assumption, but you realize by going through this, if you're looking at a problem where you don't need a power series for, like a power series was just overkill, and maybe like a polynomial could solve it, some finite polynomial, the power series is actually going to tell you when you're in that scenario, like it told us here. We actually don't need an infinite number of terms. It turns out that a finite, so a cubic equation will actually solve this ODE. So let's look at the solution. A0 plus A1x plus A2x squared plus A3x cubed solves the ODE. Where these guys are just going to be whatever the initial conditions are. My A2 was minus 3A0. And my A3 was minus a third A1. So now if you give me initial conditions, I can tell you exactly what quadratic is going to actually solve this ODE. But that's the solution. And I mean, yeah, you could write it as like A0 times 1 minus 3x squared plus A1 times x minus a third x cubed. But a finite polynomial solves this ODE. For n greater than, no, not for n greater than 2. I know it seems that way, but I'm measuring this subscript here. The n here is what I need to plug into the n, as it says here, is the guy that's I'm plugging on the right side to compute the guy on the left side. So when I say for n greater than 4, I meant to write greater than 4. Your a sub n is going to be 0 for your n greater than or equal to 4. Right, because it's a sub n. Right, so I found that a sub 4 is 0, and everything beyond that is going to be 0. So all the way up to a sub 3 is actually non-zero in general, unless someone gave me like zeros for the initial conditions. If the initial conditions were both 0, then y equals 0 would be the only solution to solve that. All right. Yeah. So those were the two examples. Now, hopefully you guys were trying this by yourself at home, and hopefully that was clear. What I want to do now is talk a little bit about this thing that we noticed over here. The fact that sometimes we got into a situation where we had to evaluate terms. This is officially one of the steps that I put in the box. That you have to make sure that all your series start at the same point in order to combine them, because theoretically this is what we needed. However, there is an option out there for which we can just not actually care about where the series starts. So this is going to lead us into a section that I call advanced, but advanced in quotes. It's not actually that crazy advanced, but it does make things a little bit easier by getting us to look at things slightly differently. So whenever you go into a class called, by the way, the method that we're talking about here is called the Frobenius method. This is when we solve an ODE using power series. The general theory for doing that was developed by this mathematician named Frobenius. So it's called the Frobenius method. So I can actually generalize the Frobenius method a little bit by using something that's a little bit more generalized than a power series. Whenever you go into a complex analysis class, you're going to hear about something called a Laurent series. Okay. Now, what you can think of as a Laurent series is it's a power series that actually goes in both directions. So it's actually a series that, yes, it starts, if you look at this guy. Yeah, there's an a0 plus a1x plus a2x squared plus ... But it's a series that also counts backwards. So there will be an a minus 1 x to the minus 1 plus an a minus 2 x to the minus 2 plus an a minus 3 x to the minus 3 plus ... So extend your definition of a power series to also cover the negative exponents. Okay, now this is actually super important. And in complex analysis, the reason why complex analysis works out so nicely is you really realize that a lot of things developed can be determined by this term here, which is called the residue of the function. And it turns out that in complex analysis, you can use that guy to solve all sorts of problems. In a lot of complex scenarios, all the terms diverge off, go off to 0 and leave this guy as the only guy that's standing. And it turns out that that actually leads to a lot of nice things. Anyway, we're not going to worry about that. We're just going to think of our power series solution as being a Laurent series. However, to make it coincide with our power series solution from the previous section, we just define that our a sub n is going to be 0 whenever our n is negative. So it automatically assumes that the a sub minus 1, a minus 2, a minus 3, it assumes that all those coefficients are 0. Okay? So I think of it as a series that goes off from negative infinity to positive infinity. But then I just define that all the coefficients of the terms of that all the coefficients of x to a negative power, those guys are all automatically 0. And so I really get a power series solution, but I get it in a way that's going to be beneficial. Now, here's what we can do. We can continue as previously, except you do not need to evaluate terms in order to get series to start from the same index, because I'm going off to negative infinity, right? So whether I start 1 step ahead or 2 steps ahead is irrelevant. Like that means you're 2 steps further into negative infinity. It does not make a difference. So by thinking of my lower bound for the series as going off to negative infinity, I can shift people around at will and never have to worry about correcting the index, right? So in some sense, I can even just ignore the indexes altogether. So let me actually show you what this would actually look like with the example from the final, where we actually don't have to worry about the indexes. And I'm going to also mention something here about the radius of convergence of the power series solution later on. Okay, so here's what we can do is assume our y has this solution, n equals minus infinity to infinity of an x to the n with an equals 0 if n is less than 0. Okay, now this is equivalent to, so this is equivalent to a power series. So this whole thing here is equivalent to a power series. But it's more convenient. We can, from now on, ignore the indexes. Indices, plural of indexes. Index, right? Because I don't care what the n values are because they're going all the way down to negative infinity. It really does not matter where the indices start. So I can, at this point, I can even just write the sigma notation and completely ignore, just not even worry about indexes at all, indices. And then I would actually get an equivalent solution. So here's what that would look like. So I'm just going to go in and I'm going to actually plug this in. So this leads to 3 minus x times the series, and I'm ignoring the index, n times n minus 1, an x to the n minus 2 plus x squared n x to the n minus 1 plus 1 plus x series an x to the n. Okay. So all of these guys have index from negative infinity to infinity. And I'm writing this down for emphasis, but in general now we don't even have to care about this because now the lower number is going to be, if I shift n's by n minus 1 or n plus 1 or whatever, it's not going to make a difference because I'm going down into negative infinity. So from now on I can completely ignore indices, and I would get a series of 3 n minus 1 an x to the n minus 2 minus the series n minus 1 an x to the n minus 1 plus the series n x to the n plus 1 plus the series an x to the n plus the series an x to the n plus 1 equals 0. Now I do need to still make sure that the powers start off the same, so I'm going to shift these two guys here. But again, I don't need to care about the indices. To shift this guy. Okay, so I shift all n's to n plus 2's in the first series, shifted all n's to n plus 1's in the second series, shifted all n's to n minus 1's in the third series, left the fourth series alone, shifted all n's to n minus 1's in the last series. Now all of those guys have power n's. As for the indices, I do not care where they are. I can just bring everything into one big series at this point. So I have that. And then I immediately jump down into the recurrence relation. Now remember, the recurrence relation automatically helped me to find, and I mean, the recurrence relation is going to look like, it's actually going to be the same guy that we had here. This was that problem. So it's that, right? So again, this canceled that term when I multiply it out. So then I can move those guys over, and then I would end up with that. All right. And we can continue. But again, this is just a repetition of last time. So we saw that this was the answer here. Not going to go over it again. Right. So that's it. That's the variation on this method. So just assume that you have a Laurent series, which is just a power series that counts down into negative infinity, which, yeah, actually works, actually is convenient a lot of times, and actually is very important to complex analysis. Yes, it will work for all questions. If a power series solution can work, then a Laurent series solution can work, because we also make the assumption that our coefficients are zero whenever the powers go negative, which means we're essentially ignoring the negative part of the series anyway. The part of the series with negative powers are being ignored. So yeah, this is going to work in all cases. Because regular power series are more convenient. Remember, when your x's have negative powers, in general, that could be bad when your x hits zero, right? Remember, a power series was just a generalization of a polynomial, which is why they were very nice to deal with. Once you go to the negative side, you go to the dark side, you can't look like a polynomial anymore. You now have points where your function is undefined. So it's not continuous everywhere. There are issues with this in general. Essentially, we just developed this for situations where it's going to be convenient to look at the world in this way. Kind of like how a lot of the times we solved quadratics, finding the real solutions, but eventually we got to a point where, you know what, I want to be able to solve x squared plus 1 equals 0. Let's invent something that allows me to solve that. In the same way, that's this kind of thing. So the power series are the nice thing, but then we're like, the power series doesn't cover all cases that we want to talk about. So let's invent a generalization of a power series that can work. And the Laurent series is that generalization. But theoretically, it allows us to ignore a lot of things. So that's why. I don't want to be able to just say, oh, for a power series, you can just ignore all this stuff. Like, I don't want to be able to say that. We have to have some mathematical backing. Why is it mathematically legal for us to ignore where the series started from? And if you put a Laurent series in the theory in this way, it allows us to ignore a bunch of stuff and still come up with the exact same answer that we would have came up with had we paid attention to all the stuff. So it actually does cut down your work a little bit. And you'll realize if you went through a bunch of problems already where you had to evaluate terms to get all the series to start at some point, go back and do all of those problems where you're just ignoring where the series started. You'll realize that you got all the same answers, and it'll be shorter because you're ignoring like a whole set of calculations. So that's one variation on the technique. Technically, though, this series is only viable in a complex analysis scenario. It's not viable. It's really useful in a complex analysis scenario, but we can use it in the real analysis part when convenient, and just pretend that all the terms that would not make it a power series, just pretend all those guys are zero, and you get something really nice. Here's some that I want to make sure that we can answer, and this kind of goes back to a problem that I asked in the quiz as well. If I were to ask you the following question: what is the radius of the power series solution that we just found? Radius of convergence. What would you say? Like if I were to write down an infinite number of terms, write down all the terms, not just the first four, right? So this is some sort of power series here, right? So this is going to be some sort of power series, a n x to the n, right? So this guy, if I wrote down in general, what is its radius of convergence? And let me emphasize, as a solution to the ODE. So I don't want you to just look at this as a series in isolation and give me the power series, the radius of convergence. But as far as its ability to solve this ODE is concerned, on what interval or radius can I think that this guy would actually give me an answer? Notice that for this problem, we were centered at 0, 0. At 0, x equals 0. So the series is centered at x equals 0. The ODE is x squared 1 plus x. Okay, so now this is combining some of the things that we spoke about before in theory. Okay, so that's my ODE. What are the intervals where a solution would exist? So let me ask you that. So for this ODE, intervals where a unique solution would exist, according to the existence and uniqueness theorem. Where can I find a unique solution to these guys? X equals 3 and x equals -1 is not an interval. It turns out that the intervals where you can expect a unique solution to exist is all the intervals that don't contain 3. Since in standard form, which is how the existence and uniqueness theorem considers the ODEs, the ODE is, well, y double prime plus x squared over 3 minus x y prime plus 1 plus x over 3 minus x y equals 0. And so a solution is only guaranteed to exist and be unique on any interval where the coefficients are continuous. You'll notice that the coefficients in standard form are not continuous at 3, which means my solution cannot involve 3. However, we are centered at 0, which means if I start a power series solution centered here, the radius it can extend to is up to this point. So my power series is only going to work in this window here. So the ROC is 3, and the interval of convergence is from 0 to 3. The power series cannot extend beyond 3, because it will extend over a point where the ODE has discontinuous coefficients. So on the quiz, when I asked you something about the radius of convergence of a power series solution to an ODE, basically what you had to check was find the points that made the first term 0, and then based on where the initial conditions were, just figure out what is the largest amount that you could extend before you hit one of these points. And that is going to be where your power series solution is going to work. Now, it turns out that if you're on the other side, a completely different solution might emerge, where it's a whole different power series that you would get. All right. So if I centered my series at 4 or something like that, then I would have a power series centered at 4. I would have x minus 4 raised to the n, and I'd have a different set of ANs that will give me the solution in that case. And then I would have a completely different solution on the other side of 3. And if I centered it at 4, the radius of convergence for that series would only be 1, because I would only be able to extend back until I hit the 3. So the series over here, the solution of the series over here versus the solution of the series over here are different solutions. I can guarantee that both of them are unique, but they're only unique on their interval. If I went to another interval, I might have a completely different solution, but there's a unique solution on that interval. So that's very important. I don't know what you mean, give an example of how to tackle that question. I just showed you how to tackle it. Find where your power series is centered at, and find where all the bad points are, and make sure that your radius of convergence does not extend beyond one of those things. So I believe on the quiz, it was like a half was the answer. Like if you extend a half a unit, you'll hit a point where the ODE messes up. If memory serves, I don't remember. But it was the kind of thing that you would look for. Here's another thing that we can do with series. So this is another technique. Yes, we got initial conditions. If you read the thing here, it says y of 0 was -6 and y prime of 0 was 2. So we were given initial conditions here. We were told that we're at 0. Which is why the assumption was the assumption is y equals a series of a n x minus x naught to the n. Now in this case, because of this and this, those tell you your x naught is 0. So that gave us that our solution, the assumption, should be just a n x to the n. And so now I found that solution, that power series solution in that form, and it's this guy. But then we might ask the question, where is that solution valid? Does this solve this ODE on the entire real line? The answer is no. This solution is only going to be valid on the interval from actually -3 to 3, because it extends in both directions. It's a power series. Right, and the reason is because if we hit x equals 3, we get undefined. Now, if you told me the series was centered somewhere else, you'll have a different radius of convergence. You'll have an entirely different series altogether. Okay, yeah, I don't remember the exact problem I put on the quiz myself, so I would have to look it up, but I'd rather like move on. But if you go back in the quiz and try to look at it with this lens, and you should see the answer that way. Here's another way to find a series solution. You can actually use what we know about Taylor series. So remember when you were, this is again way back in Calc 2, but you can you can generate a power series for a function by using Taylor's formula. This means you assume that the coefficients look like this, right? So, I mean, you might remember this from Calc 2 in the form. So from Calc 2, you kind of looked at it as the series of f to the nth derivative at x naught, x minus x naught over n factorial. This was what we got for a Taylor series. So this guy here is your coefficient. Right? And so that's how you could actually, you can find a coefficient. Now, of course, you learned in Calc 2 that this doesn't always converge on any meaningful interval, and it doesn't always converge to the function that generated it. However, let's assume for the sake of argument that our function does have a Taylor series expansion. We can write it as a power series in this particular way. It turns out that this gives us another way to actually find the coefficients. This literally gives us a formula that generates the coefficients. You can think of this in and of itself as a recurrence relation, right? So you could actually say an equals f to the n at x naught over n factorial can work as our recurrence relation. And so that gives you just another option. Let me actually show you an example where we can take this idea and develop something very nice. Look at this ODE right here. We are going to assume that that has a Taylor series solution. And we're going to find it. Now, you can immediately see that this is going to be very complicated to do based on what I've told you before, prior to this. Because the sine x and cosine x are their own series. They will expand into a series on their own, which we'll have memorized. But at the same time, if I have the series for the sine times the series for the y prime, to actually multiply that out and figure out what series that's going to be forever. That's going to be crazy. So we probably don't want to do it the way that I showed you before. There is another option. If we assume that there is a Taylor series that will solve this, meaning a power series that conforms to this kind of construction, then we can get something else. So here's how that would look. So here, notice I have y of 0 equals a0. Now, so that's my a0. Y prime of 0 equals a1. Okay. What would y double prime be? Now, from the ODE, y double prime, if I were to solve for that, that's going to be minus sine x times y prime minus cosine x times y, which means that my y double prime at 0 is just going to be, well, minus y of 0, which is minus a0. Which means minus a0, and remember, I can solve for my an here. So this means my whatever, my a0, this means a2. I'm using this new formulation here. So if I use that formulation here, so my y0 and my y prime of 0, those guys are given initial conditions. For my y double prime at 0, I actually solve for y double prime and plug in 0. Then I get minus a0. But remember, y double prime at 0 is what? Y double prime at 0 is actually 2 factorial times a2. This means that minus a0 is 2 factorial times a2. This means that my a2 is going to be minus a0 over 2. And I can actually continue with this construction. I can go to y triple prime. I can differentiate this. So differentiate the sign, leave the y prime, then leave the sign, differentiate the y prime, plus differentiate the cosine, leave the y, minus leave the cosine, differentiate the y. So if I call this equation 1, what I just did was differentiate equation 1 with a chain rule, product rule. Now I can plug in 0, y triple prime at 0. That's going to give me minus y prime at 0. The sign is going to go away because that's sine of 0. Sine is going to go away, sine of 0. Minus y prime at 0. So this is minus 2 y prime at 0. Y prime of 0 is a 1. But I know that my y triple prime at 0 equals 3 factorial times a3. This means 3 factorial a3 is equal to minus 2a1. This means my a3 is going to be minus 2a1 over 6, or minus a1 over 3. And we can continue, but I don't want to. So far we have a0, a1. I know that my a2 is actually minus a0 over 2. I just found that my a3 is minus a1 over 3. So this means my power series solution is going to start looking like the following. So my y is going to look like a0 times 1 minus x squared over 2 plus dot 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 plus a1 times x minus x cubed over 3 plus dot dot dot. And I found a solution, a power series solution to this ODE with some crazy coefficients that will have their own power series. And it will be really complicated to find them. So instead, I use this little formula here. Understand that my nth derivative evaluated at the point will give me n factorial times the nth coefficient. And so what I can do is I can just keep finding derivatives, keep plugging in that point, and then keep using that equation to generate my ANs. And then I just plug them all in at the end of the day. So that's another scenario. Yes. So that's another way to find a power series solution. Now, we're going to move on. But this little theorem here kind of summarizes what we've been talking about. It talks about the possibility of there being a power series solution and what it would mean to find one. But essentially, if you just know what I told you, you can remember everything that I told you even before the Taylor series point, and you'll be fine. For a lot of situations, taking this assumption so that you can ignore the index would be convenient. So if you want to just do all your problems like that from now on, that's fine. But in general, the problems that you should be able to solve is the guys like I wrote here. And just know enough about the theory to be able to answer any other questions that I could ask in a multiple choice questions like, what interval would this power series solution work on or something like that. That should be something that you should be able to figure out by just taking into account where the series is centered and where the points that will make the coefficients undefined are whenever the ODE is in standard form. Because you have to kind of avoid these guys because the existence and uniqueness theorem breaks at such points. All right, so those were the advanced, not necessarily but the advanced series techniques. Move this up a little bit here. And I mentioned here, we're going to skip a bunch of things. There's a bunch of nice equations that have very nice series solutions associated with them. They're very well known. They're highly applicable. They even have names for them, like the Chebyshev's equation or the Lejeune equation. And yeah, we're kind of going to skip that. What you need to know about power series solution is basically what I've been doing. So being able to solve a situation like what we did here, not here, like what we did here, by knowing what assumption to make for your series, plugging that guy in, shifting the powers, coming up with a recursion formula to find the coefficients. That's what you really need to know from this section. Yes. So even in a situation where you're on the exam where you're showing work, like you have to scan or throw something, for this situation, you can ignore the indices. Just make a note that this is your assumption. And then from that point forward, ignore indices, ignore where your series start, and you'll be fine. So yeah. So by envisioning our power series as a Laurent series, we put ourselves in strong theoretical foundation to be able to ignore a bunch of things. All right. So let's introduce the next guy. We're going to talk about Cauchy Euler equations, and this was started on the 8th. Now, you might recall, because this is going to be important, the definition of an ordinary point and a singular point. So remember, an ordinary point is an x value such that when I put an ODE in standard form, it does not cause a division by 0. A singular point occurs when you would cause a division by 0 by putting things in standard form. So if I have p y double prime plus q y prime plus r of y equals 0, and I divide through by p in order to put it in standard form, any value for which p is non-zero, we call this an ordinary point. Any value for which it is 0, we call this a singular point, because then if I plug in that value, I would divide by 0 in the coefficients. Now, singular points are very hard to deal with in the sense that finding a power series in the way that I mentioned to you that we've been doing over the past 2 lectures will not work if you're at a singular point. If your power series is centered at a singular point, it actually won't work. I'm not going to go into why it won't work, but basically, you'll only get a series that converges at one point, and it will only give you like the trivial solution or something like that, which there's a video of some guy doing an example where he showed you what would happen in that scenario here. So I'm not going to go over that, and you don't really need to know that. What you do need to know is that when there is when you are at a singular point, you cannot find a power series solution centered there in the way that we've been doing before. There is a way to find a power series solution, but in order to talk about that in the first place, we need to talk about something else, something called a Cauchy Euler equation. Now, a Cauchy Euler equation is a general equation that looks like this. It's kind of like when your differential equation coincides with an nth degree polynomial. So you have an x to the n times a y to the nth derivative, and an x to the n minus 1 times a y to the n minus first derivative, and all that stuff here, where our AIs are constants. Right? Now, we are going to care about the second order version of this guy. And the second order version is just called an Euler equation. So whenever we're in differential equations and we say an Euler differential equation, we are talking about a differential equation that has this form specifically. It looks kind of like a quadratic merged with a differential equation. Alpha x squared y double prime plus beta xy prime plus gamma, this is gamma, which I know it kind of looks like a y, but it's really like a loop at the bottom. Gamma y equals 0. This is called an Euler equation. It's pretty much a second order version of a Cauchy Euler equation. So the Cauchy Euler equation is the general nth order one, but when we're down to a second order, we don't need Cauchy. We only need one mathematician to handle this. Right? So it's like with these theorems, the more names of mathematicians attached to the theorem, the more like badass and comprehensive it is. When you start cutting off mathematicians' names off of something, it just makes it simpler. Remember Gaussian elimination and Gauss-Jordan elimination from linear algebra? Yeah, you guys will know what I'm talking about. Okay, so it turns out that this kind of equation here, you will notice that x equals 0 is actually a singular point. And we'll get back to that later. Note, x equals 0 is a singular point here. Now, it turns out that we can find a non-power series solution at this singular point. And we're going to use this idea to be able to figure out how to find a power series solution around a singular point. Well, a certain kind of singular point. We'll get to that tomorrow. So basically, here's how we're going to do it. We're going to make a guess, because that's how we do this in differential equations. That's what we do. We're going to guess that our y has a certain form that will solve this. Now, guessing that y equals e to the RT is not going to be as efficient or as obvious, because we have polynomials here. We have an x squared and an x and blah, blah, blah. So a better assumption, one that can be more efficient, even though the exponential assumption would work, it'll be a lot harder to work out the calculations. a nicer assumption is to think that your y is actually a power of x. Think of your y as something like x to the r, where r is a constant that you can determine. So think of that your y's are also powers of x's. So now when we plug them in here, we can get like terms that we can combine and cancel each other to get 0. So if your y is x to the r, then your y prime is going to be r x to the r minus 1. Your y double prime is going to be r times r minus 1 times x to the r minus 2. Plug that into the original ODE. Plug that into 1. You would get this thing here. You'd be able to factor out a common x to the r. Right? Because here you get the x squared times the x to the r minus 2. That will become x to the r. The x times the x to the r minus 1 would become x to the r. So you get x to the r as a common term. You can factor out x to the r. Then we're going to assume that our x is non-zero because otherwise our y is 0, and that's just a trivial solution. And we can get that by plugging in our coefficients for the homogeneous term to be 0. So let's say we want to find a non-zero solution. So we assume that our x is non-zero, and we divide through by x to the r. That leads us to this equation right here. This equation is called an indicial equation. It's called an indicial equation because it gives us the index of x. It's also called an indicial equation because it's going to be the thing that is going to modify the index on a series later on. But that's too much foreshadowing for once. Once you get this equation, that you'll notice is a quadratic, which we can solve. And again, we get 3 scenarios. Either there's going to be 2 distinct real roots, there's going to be 1 repeated real root, or there's going to be 2 complex roots. And we get 3 situations, which I have summarized how to deal with those situations here. So this is going to be very similar to second order ODEs with constant coefficients. Right here, the coefficients are not constant because there's an x squared attached to the second order term, there's an x attached to the first order term, and there's just a constant in the linear term. However, we can, by making this assumption y equals x to the r and assuming our x is non-zero, or specific, I'm going to talk about greater than 0 at first, then I'll talk about non-zero. By solving this equation, we can get various solutions with these 3 cases. If there are 2 distinct real roots, then you get x to the r1 and x to the r2 are possible real roots. So a linear combination of those is going to be the solution. So we get the first scenario, y equals c1 x to the r1 plus c2 x to the r2. If you have a repeated root, you will get this being the solution. Y equals x to the r plus c2 x to the r ln x. Now, where that ln x comes from, essentially it's reduction of order. And I explained a little bit down here into how you can think about it. Think of the x to the r as an exponential. You'll realize it looks like e to the rt, except your t is replaced by an ln x. So just like how we would multiply the second solution by a t in the constant coefficient case, we instead multiply by an ln x in this case. And that's how this guy works. So you get the x to the r, and then the second solution is given by ln of x times x to the r. If you have a complex solution, it breaks down into this whole thing right here, which again, by thinking of this in terms of exponentials, rewriting this as an exponential, that is going to make sense because I guess I need to talk about it here. If you look at this guy, if I have x to the a plus ib, this is just x to the a times x to the ib. This is just x to the a times, I can write this as e to the ln of x to the ib. Well, that's just going to be e to the ib ln x. And then I just think of the b ln x as the coefficient of I. Apply Euler's formula. So that's going to be the cosine of b ln x plus I times the sine of b ln x. And that's how you get this kind of solution looking like that. Okay, so that gives you the other version. right? So you have three distinct situations here. And again, this is in a box. You do have to know this. So for this particular kind of equation called an Euler's equation, you can set up what's called an indicial equation. It serves the same purpose as the characteristic equation. Based on the roots of that indicial equation, you will be in one of three cases. And the solution based on those cases would be like this. In the event that we want to cover the case where x is less than 0, here we have an ln x. So if our x is less than 0, that's a problem. Turns out you can fix this by just replacing all x's with absolute value of x. So for x greater than or less than 0, but not equal to 0, your solutions will look like this. I just went everywhere and plugged in absolute value x for x. And it turns out that because of the derivative of ln of absolute value of x is the same as derivative of ln of x, this also works out. So here are some examples. I will do the first one. Then you guys can try the others, and we'll pick up with those guys tomorrow. And then I'll show you how to use series. So here I'm going to do this one. Try the others tomorrow based on this, and we will continue with those. So here, notice that I have the x squared term on the y double prime, the x term on the y prime, and the constant term on the y. So this is like an Euler equation. With my alpha equals 1, my beta equals -4, and my gamma equals +4. So what I would do here is find the indicial equation. It's alpha r minus 1 plus beta r plus gamma equals 0. So this leads me to r times r minus 1 minus 4r plus 4 equals 0. This is r squared minus 5r plus 4 equals 0. And that's a quadratic, and that guy factors. -4 and -1, it looks like. So now notice that I would get r equals 4 or r equals 1, which leads me to the assumption, since my y was x to the r, it's c1x to the r, which is 4 in one case, plus c2x to the 1 in another case. And I put the absolute values around these. Now x to the 4 is going to be fine without absolute values, but make sure I leave them on here. And that's it. So this is another very quick type, kind of like it has a feel like the ones with constant coefficients. Just based on our assumptions, we get a lot of things for free, and we have a very nice general strategy to actually. We get a very nice general strategy to actually solve guys that have this form up here. And you guys are going to go off and try those for next time. So I'll leave these guys here for you guys to try. And we'll pick up with these next time. Then we'll go on to solving series solutions near singular points. Oh, the absolute values is because there are a couple of reasons. Because we're assuming it's x to the r, our assumption is our y equals x to the r, which means when your x is negative and your r is maybe like a root, an even root, then you know, like your r is a half or something, then you'll get complex numbers coming into the mix. So when your x goes negative, it will cause issues. It also goes negative because of the ln x in the solutions here. And so ln of a negative is undefined, and so that's why you make x's absolute values and it'll actually work out. So because your x is not 0, we can just use absolute values. In the case where they tell you x is positive, then you can leave it as x and it'll be fine. So we need absolute values around the x because the logs and power functions misbehave when your base is negative. Now, you guys can try that. So in terms of the next exam, so the 17th seems to work for almost everybody, but I don't know. What about the 18th? Was it only one person that the 18th could not work for? So I believe it was Ophir. The 18th was bad. Is there anyone else? Okay, so we'll let it be the 17th. Also, test 2 is on the 17th. Pretty much the same kind of deal that we did last time. All right, and with that said, we're going to wrap up here. So I might even leave up the notes for the series. No. So we'll do it on Friday, and what's on Thursday is not included. So only what's up until Wednesday will be what you need to know for the test. What I do on Thursday, which will be the last topic in the entire course, believe it or not, is going to be, I'll leave it as like a bonus or something. But we will wrap up there. I will leave all the notes. I'll leave the examples that you have to do. I'll also leave the notes for the series version. So if you guys want to get a head start on that, you can. And oh, is homework due on Saturday? Well, yeah, I'll move anything. I'll go check on the homeworks right now. Make sure I'll adjust the dates. All right. With that, we will end there. And this is Jhevon signing off. I will see you guys in the next one. Ciao.